you're trying to separate the x's and the y's on this one, one thing I might do to start is multiply both sides by the dx. That would give me dy equals y squared dx. But the goal is to get the x's on one side, the y's on the other. We haven't achieved that goal yet. So I might take this y squared here, divide that to both sides. That would allow me to move it over here. Now if I'm dividing by y squared to both sides, dividing by y squared is the same thing as having y to the negative second over here. Right? If I had dy over y to the second as I divide, I could just rewrite it as y to the negative second dy. And then you got your dx left on this side. So we've separated the y's from the x's. Once we do that, because we're starting with a derivative type scenario and we're going backwards, we're going to take an antiderivative here at some point. So we take the antiderivative when we separated the x's and the y's. I take the antiderivative of the left side here, adding 1 to that power, I've got y to the negative 1 power. Take the reciprocal of negative 1, which is negative 1, place the negative 1 in front. That's going to equal on this side, well, let's think about the function I'm taking the antiderivative of here. Technically there's a 1 right there, right? So if that's just a constant, you're taking the antiderivative. The rule with constants are you attach the variable, so we attach an x to that 1. So 1x is the antiderivative there. We've taken the antiderivative as much as we can on each side, so need to incorporate the constant somewhere. So usually we just tack that onto the right side, but it doesn't matter. Make sure you're tacking onto one side or the other. And normally the reason we tack it on the right side, especially when you're dealing with y's and x's, is you're trying to isolate the y expression as much as you can. Now, there's not much more we can do here except maybe rewrite this so it's negative 1 over y to the first equals x plus c. But the y expression is by itself on its respective side, and the understanding is if I took the derivative of this right now, use some implicit differentiation, solve for dy dx, eventually I get back up here. So that's my answer as far as this differential equation is concerned. So if we cross multiply to get started, you got dy, you got a y squared. I could say y squared dy on the left side of the equation. Got a dx multiplied to the x squared square root of x cubed minus 3, so I could write x squared square root of x cubed minus 3 dx on the right side of the equation. Just so happens by doing that, we separated the x's and the y's. So since I've achieved the first goal there, now I can take the antiderivative of each side. Taking the antiderivative on the left-hand side of the equation, you've got a y squared, so we add 1 to that power, you get y cubed, reciprocal of 3, 1/3 would go in front. And that's going to equal, all right, we need to recognize here on the right side that we do have an issue. Right, this is not set up in a form that we can take the antiderivative efficiently right now. In fact, we're going to have to use some U-Substitution. Right, we've got this root involved, so I should let u equal the x cubed minus 3 under that root. That means on these problems, since we're taking antiderivatives at various points, we do have to remember all the techniques that we have for taking antiderivatives. U-Substitution may come into play. As I've said before, if we introduce a new variable, we've got to set up a new problem. So we haven't taken the antiderivative yet. We've introduced u as x cubed minus 3. That was under the root, so I'm going to write u to the 1/2. That's this piece of it, meaning I still need to replace the x squared and the dx. So we understand that's where we take the derivative up here. we get du equals 3x squared dx. And if I'm trying to replace an x squared and a dx, just divide 3 over. Got 1/3 du equals x squared dx. There's that combination I'm looking for. So take the x squared and the dx out, put the 1/3 and the du in. Got my new problem now. I can take the antiderivative of. So as I do that, still got the 1/3 y cubed over here. Taking the antiderivative of 1/3 u to the 1/2, you've got 1/3. That will be multiplied to, well, let's see, if I add 1 to that power, that's 3/2. So that's 2/3 that gets multiplied to the front. That's as much as I can do with the antiderivative there, so I'm going to tack on c. And now to clean this up, still got my 1/3 y cubed on the left side. Obviously going to multiply these together, make that 2/9. But we started in terms of x and y. We need to end in terms of x and y. So I'm going to take this u back out, replace it with what we let u equal up here, the x cubed minus 3. That will be raised to the 3/2 power, and then tack on your c. Now at this point, acceptable answer. Like I said on the last one, the idea is if I took the derivative of this using the implicit technique, at some point solving for dy dx, I'd end up back up here. But oftentimes you might see fractions being cleared out, so you could multiply, say, everything here. Since we've got a 3 and a 9, you could multiply everything by 9. And if you multiplied everything by 9, then you'd have, well, over here, multiplying by 9 would be 3y cubed. Over here it'd be 2, because the 9 would cancel out, times the quantity x cubed minus 3, raised to 3/2. And then you could say you're multiplying by 3 of this constant, but you're still getting a constant, so we're going to use c still. Ideally, either of these would be acceptable answers. Yeah, if the goal is to get the x's on one side, y's on the other, we can do a couple of things here. We can multiply both sides by dx, clearing the dx from the left side, swinging it over here. But we can also FOIL the x plus 1, the x plus 2. So if I FOIL that out, get x squared, outside's 2x, inside 1x, so that's going to be plus 3x, and last plus 2. So we've separated the x's and the y's, we've simplified the x side of it. We can take the antiderivative now. I'm taking the antiderivative of the left side. It's kind of like the first problem we did. There's that 1 in there. So since 1 is a constant, we're taking the antiderivative with respect to y. All we have to do is attach a y. So 1y would be the antiderivative there. That equals, right side is set up pretty nice for us. For that x squared, I can just add 1 to the power, get x cubed. Reciprocal of 3, 1/3 goes to the front. Plus, got x to the first here, so that's x squared. When you add 1 to the power, reciprocal is 1/2. Multiply the 3 in front, get 3/2. Got your constant of 2, so that's plus 2x. You've completed the antiderivative process, so we tack on our constant. Okay, this problem does have additional information, and because it has additional information, that means we can figure out what the constant value is. We're also given that y is negative 3/2, and x is negative 2. So we'll plug in negative 3/2 for y. We'll plug in negative 2 for x. all that's left now to solve for is c. So we got a little fraction party going on here. Okay, so hashed out the fractions. C equals -5/6. Since we know what c is, we're trying to solve for this differential equation. We need to go back to our step right there. Plug in c. We'll have y equals 1/3 x cubed plus 3/2 x squared plus 2x, and then minus 5/6, our value for c that we found.